Day 7, Advent of Code. Um, I just finished streaming that. So, if anyone doesn't know, I'm streaming pretty much every day of Advent of Code, starting from day 4 because I didn't think of it for from day 1, 2, and 3. But I streamed day 7. So, if you want to see the thought process on how I do it, check out that video. But today's results on day 7 was pretty good. I scored 3,785 on part 1. Pretty good. And then for part 2, I solved it within like 4 minutes because it's a very small extension. And I placed under 3,000, which is my best score. These are two of my best scores. So I'm pretty happy with my scores. I'm like being able to do under 10K rank for all of them. But let me explain how the solution actually works. So let me throw up Excalibur and I'll run through the code. And I'll post all this code on GitHub too. Let's look at number 7 right here. So basically, I'm just going to read out the prompt and then so you can kind of figure out while I say it. So the historians take you to a familiar rope bridge over a river in the middle of the jungle. The chief isn't on this side of the bridge, though maybe he's on the other side. So like we're stuck at a specific bridge, but that doesn't really matter to solving the question. So when you go to cross the bridge, you notice a group of engineers trying to repair it. Apparently it breaks frequently. You won't be able to cross until it's fixed. So you're trying to cross some bridge and you ask how long it'll take. The engineer tells you that it only needs final calibrations. But some young elephants were playing nearby and stole all the operators from their calibration equations. They could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations. It's a bit wordy, but essentially, you're given a bunch of rows of different equations here. And you just want to see which one of these can ever equal the element on the left. And the only operations that you could introduce are multiplication, or plus. So basically, you can go in and like add a plus here, and that doesn't equal 1990, right? But if we do multiplication, like that, 10 times 19 equals 190. So like you can use different combinations to get to 190. And then this one as well, 3267. You could try a plus here. You can try a multiplication here. Does that add up to 3267? No, it doesn't. Should we try like adding a plus here instead? Does that equal? No, it doesn't. Like basically the solution is trying every single possible combinations of pluses and multiplications between the two terms. So we have 2 slots that we want to try out different one, and we try out all combinations, and then we pretty much multiply the terms and figure out what the result is. And if that result equals that, we're good. The way you solve that a lot of times is with the backtracking algorithm, but let me just see I don't miss anything. So each line represents a single equation. The test value appears before the colon on each line, and it's your job to determine whether the remaining numbers can be combined with operators to produce that given value. So we want to combine these terms and use some sort of operations to build that value. Operations are always evaluated from left to right, so you just need to perform pluses and subtractions from left to right. What else? So that pretty much what it means left to right is like I put multiple times here. Like a lot of times if I do multiplication times, sorry, that stroke width is so weird. But essentially, like pretend if I do, let's just do add a plus here. Pretend I do plus here. I'll do multiplication here. I'll do like a lot of times in school you learn that you have to do multiplication before addition, like with that BEDMAS stuff. But this one's saying you always have to do it left and right. So you always have to go 6 plus 8, then take that result and then multiply it by 6, then take that result, then multiply it by 15. So you don't have to do anything fancy. That's what makes this question a lot easier. What else? So it's evaluate from left to right and can only be pluses and minuses. Only 3 of the above equations can be made true. So it shows an example, like 190 can be made true because you can multiply 10 and 19 to get 190. 3267 has, like, this evaluates as true because we're able to, like, plus 40 and then multiply that result by 27 to get that value. And then the other ones you don't return because, like, you don't care about because you can't use any combination of operators to get to that possible value. Yeah. Cool. And then pretty much what you have to do is, if these terms, you can place operators to get that specific value, you have to find all the lines where that's valid, where the right terms can be created. I mean, can be like, there's some permutation that you could combine these terms with some permutation of operators in order to get a value. You pretty much add up all those lines that are valid, and then that's how you return the final result. So how you can do that is using like a backtracking algorithm. So pretend I want to see this 3267, right? I want to see if 3267, we can get to 3267 using these terms. So we say we have to evaluate from left to right always, right? So we start at the very first element. My first part of the code actually, like, what does it do? It splits the value we want, and then it grabs this side, and then it turns that side into an array. So it turns this side into an array. So it basically takes, like, what we do is, like, we take this, we split it, and we turn this into a target right there, and then we build an array for the results here. Right? Now we pretty much have this array. All we literally have to do is start at 81 because we're moving left to right. And then from 81, we put 81 there. And then we move on right away to 40, right? There's 2 ways to use 40. 2 paths here. We have 40 here, 40. Then we have 27. Oh, sorry. There's two ways that we can combine 40 with the first term. We could either add like that, or multiply like that. Right? What does this actually equal? 81 times 40. Where is this? 81 times 40. We got 3240. Okay. 81 times 40 equals this essentially. 81 plus 40 equals 121. Right? So that's the most ways that you can combine the first two. Now you move into the next one, 27. So that splits out into like 4 more branches. Like if you added 40 to the last one, now you can try, like, you can get a different operation if you like multiply with that result, or if you add 27 to that result. So it creates like a few more paths here. So let's see. Multiplication. Add here. Multiply here. So let's take 3240, and then let's do 27 here. Right? So we can either like go down this path where we plus 40 and then we plus 27. What does that equal? 81 plus 40 plus 27 equals 148, right? Now we pretty much used up all the terms. So we get 148 here, and it's still not the target. What's 40 times 27? 1080. 1080 here. What's going on? wait, to come back to that tweaked. There you go. So we get 1080 here. What's 40 plus 27? 67. Or sorry, 32. Sorry. What's 120? What's 40 or 121 times 27? Sorry. Three two six seven. Right. Because we're multiplying, because adding 81 plus 40 is 121 times 27. So now we already hit the target. So we know that there is some combination of operators that we can use in order to get this result. So that's exactly what it says right here. 81 plus 40 times 27. 81 plus 40 times 27 equals 3267. And if we let this keep running, what's 3240 plus 27? This one also is 3267. And you can see here it also says, what does it say here? Here it also says that you can do 81 times 40, 81 times 40 plus 27. Yeah, and that leads the result. So you can see like there's two multiple ways, but all we care is that there's one possible way that you can configure these operations to get that value. So yeah, pretty much that's my algorithm. First, I literally parse out the input, so I get the target and I get the array. So I'm getting the expected results and the elements. Then I'm turning all the terms into integers. And then finally, I do a backtracking algorithm. So that's what I'm doing. The backtracking algorithm starts with the very first element. And that starts as the node right here. And then from there, when we backtrack, pretty much our target is 3267. And once the index equals the length of the elements, because we pass back these elements, basically these terms, once it gets to the end, that means that we used up all of the possible elements here. And pretty much, yeah, once it equals that, then we check, did the current sum equal the target? If it did, we return true. And then that's the very base case when we reach the array. With all backtracking recursive algorithms, you just want to define some sort of base case. Otherwise, we take the current, like 81. So we pretty much had 81 here. So we put that as the start and we backtrack on like the next element of the index or of the array. So we're backtracking on this and we're looking for the different ways we can apply 40 to like the current sum. So the different ways that we can do that is like by adding. So we take the current sum and we add the element and we move the pointer up so it's pointing at the next one. And then, or either we multiply, right? And if any of these paths ever return true, we return true in general. And then this is like the final, if any of them were true, we increment the result. So that's kind of how you solve question 1. It's a backtracking algorithm. Think of it like pretty much like if you look at this code really closely, you'll see that it's like building up this tree. So it's trying this path, so like more doing like a depth first search than building up this path and going that path. And anytime if it catches the target, it returns true. So that's how you solve question 1. Question 2 is like a very, just like I literally had to add 2 extra lines to get this, or 1 extra line to make this work. I just added this line. So all it's saying is that we're adding an extra operation. So essentially that's just like an extra path here in this thing. And the operation is basically concatenating the 2 strings. So 12,345 would become 12,345, right? So 81 here concatenated with 40 would become 8. Let me just type that. 8140, right? So we just have to add this extra path. Let's say this is this, right? But that just like makes the algorithm a lot slower because it's like 3 to the power of n now. So it's an exponential algorithm. But yeah, all you have to do is add this extra operator. And what that does to the tree is for every branch here, there's just like an extra branch. Maybe it'll concatenate 340 with 27. So we get 3240, 27. But we still let it run all the way to the bottom. and then see if that result equals the target. So pretty much you just add that. Then you add like or concat. And I'm going to post all this code now. Let me just do that right now on this thing. But yeah, that's how you solve it. Hopefully you learned something. You can watch me like quickly get this up on GitHub. Actually, I need to post this video first anyway. So I'll see y'all in the next video.